Jezza, Jeremy Murray Wakefield, here he is, has done an incredible amount of stuff. He's written seminal articles on how to mix a pop song. He's worked on the Symbian operating system, worked on the Scion series of handheld devices. Here he is speaking at the Audio Developers Conference. I went back to see what happened to dreampoint.co.uk. Doesn't exist anymore, but the Wayback Machine has still got links to it, and you can still get the source code from the original link here. And here it is, complete with his components, which of course are all C++. And although I can call C++ code from my C code, you have to write wrappers for it and what have you. I'd rather have something that was vanilla C. So I've been looking around, and this one looks quite straightforward by somebody who goes under the handle of RXI on GitHub. And this is a rewriting of Jezza's Freeverb code in vanilla C, and it looks like this. This will do exactly what I need. So downloading that. I've downloaded that vanilla C code, but I've made a couple of changes. The first is the individual comb and all pass buffer lengths. These were Jezza's original values, which were for 44.1 kilohertz. So to keep them the same length in milliseconds, I've scaled them up, because we're working at 48 kilohertz rather than 44.1. And the other change I've made is that in the structures for the comb and all pass filters, RXI, whoever they were, has statically allocated sufficient space for each comb and all pass filter. So 4096 for the comb and 2048 for the all pass. But this is very inefficient, because we only need buffer lengths of these, plus a couple of extra samples for the stereo spread. So looking at how much RAM that static allocation takes, the comb filter buffer statically allocated 4096 floats, and floats are 4 bytes. We need 8 of them, and there are 2 channels, left and right, so that's 262,000 bytes. Same for all pass, they're smaller, but so 327,000 bytes, 327k that is. And on the Pico 1 we've only got 256, and on the Pico 2 we've got 512 or whatever it is. So that's going to use a substantial amount of RAM. Whereas if you dynamically allocate them, these are what we actually need, plus a little bit of headroom, and you do the calculations, 109k. So that's a third of much RAM required if you dynamically allocate them compared to if you statically allocate them. So in here, what I'm doing is simply calloking. I'm using calloc, so it zeros it. I'm calloking each buffer to the requisite size instead of statically allocating, and that's going to save me quite a lot of RAM, which I can use for something else. And that something is Gverb, or Gigaverb, which again has been around for a long time, originally written by Juhana Sadehayu in 1999, and if this is correct, then it predates Freeverb. And this has turned up all over the internet, so it's been ported to Max for Live, and it was in Audacity, I understand. And so I'm going to try and incorporate this as well. If I've understood it correctly, Gverb or Gigaverb is an implementation of an FDN reverb, which is a feedback delay network where you've got a series of delay lines, comb filters, and they're mixed in a matrix, and then the ultimate output is mixed with some input, and out it goes. And in Gigaverb, what he's done is created comb filters and what he's called diffusers, which are essentially all-pass filters, and he's created separate left and right all-pass filters. So the comb filters are mixed together through some matrix multiplication and in the feedback path, and then the output is split into left and right diffusers to give the sense of space. Anyway, that's how I read it. I may be completely wrong, but it looks like that to me. So I've cloned both of these into here. This is Freeverb with Freeverb C and H. Gverb, which also includes an include directory with its header files. In main, I've got my types defined. In main, I'm instantiating the reverbs, Gverb, Freeverb, and my Parrot Pverb. And out of interest, I'm noting the space that each one takes up. So I'm recording the space when I start, then instantiate Gverb, record the space, work out how much that's taken, do the same for Freeverb and the same for Pverb. In the function that reads the feedback potentiometer, I'm setting the Gverb reverb time scaled appropriately and the Freeverb room size. In the function that checks the wet-dry balance potentiometer, I'm setting the Freeverb dry and wet levels, whereas in Gverb, after I've called the reverb algorithm, I'm using my own wet-dry mix to mix in some of the dry sample with it afterwards. To actually call the reverb, Gverb is called with this Gverb do, passing in the structure and the input sample, and then it's giving back left and right output sample. And Freeverb equivalent is this fv process function that's passed in the context, and it also takes a left-right sample pair as a buffer rather than separate left and right samples, but that's just the way the code's written. Then in CMake lists, I need to tell it to go look and compile these separate C files in these subdirectories, and that's about it. And then I can build it, and it builds fine with no errors. So let's run that. So as the program starts, it's printing out how much memory we started out with, so 509k. This is a Pico2, of course. Gverb has taken 330k of memory. Freeverb has taken 110k of memory, which is what we calculated earlier, wasn't it? Or thereabouts. And Pverb, my implementation, has used none whatsoever, and that's because it's using buffers in PS RAM rather than RAM in the Pico itself. So, yep, I've still got 68k to play with. Haha. The question is, what do they sound like? Well, if I flick this switch, we'll get my my Pverb, which we've heard before. Okay, so that's Pverb. This is Freeverb. Interesting. I think I might have to play with the reverb times there. And then this is Gverb or Gigaverb. I have to say I'm very impressed with this. If I just cut the input, it's got a lovely long shimmery reverb tail. Very nice. Very nice. So there you are. That is Freeverb and Gverb on the Raspberry Pi Pico.